To continue looking more at quantum theory, we're going to look at how the energy of an electron is related to the distance it is from the nucleus. And of course, we know that energy is related to color, and that's what we saw in our last video. And so in this video, let's really focus on what can we learn about the position of an electron based on color, or vice versa. All right, so here are some pictures. What are we looking at here? Well, how they first found that there were these quantized amounts of energy, because the idea that waves could have a just distinct amount of energy was a little bit hard to consider. And so what they did was they took a hydrogen lamp and a slit and then a prism. And the prism are just like anything that you might have seen in nature, or an actual prism that you can hold up that separates the light, the components of white light, into a rainbow. And so if you hold up like a prism to the sun, you're going to get a continuous spectrum. So notice in this white light spectrum, it doesn't look like there's any discrete lines that say, hey, light starts, light stops, light starts, light stops. It's just a continuous spectrum. Whereas hydrogen, helium, neon that you see here have individual lines that are showing up. And so when they held up this prism to the hydrogen lamp, they noticed, oh, not every color can be emitted by hydrogen. Why in the world is this? And so this led into thinking more about the Bohr's model that was prevalent at the time, and thinking about light and how it relates to energy. And that's really the crux of these models, okay? So with the Bohr's model, what we decided was that there's an energy level associated with each and every single electrons. N is going to be our principal quantum number, and that's going to relate to the energy level of each of the electrons. But the idea would be, as an electron gets further and further from the nucleus, it's going to have more energy. If you think of it like a ladder, if you climb up a ladder and then you fall off of it, obviously on accident, which hurts more, if you fell from the first rung or the top rung? It hurts more if you fall from the top. Why? You have more potential energy at the top, and that's going to be converted to kinetic energy at the bottom. So as you fall, you have a lot more energy. It's the same thing. Those electrons that are further from the nucleus have greater amounts of energy. So then how does this have to do with light? Well, the idea is that light is simply the release of energy. It's simply, as you go from a higher energy level to a lower energy level, you are releasing energy. How does that work in thinking back to that ladder we just talked about? Well, with the ladder, we had going from potential energy, converting it all to kinetic energy. Well, here, if you go from an outer energy region, like an n equals 5, to an inner, n equals 2, n equals 1, you don't have as much energy in n equals 1. And so where did that extra energy go? It gets released. How does it get released? As energy, which is light. Okay, so that light has a certain wavelength, and that wavelength can then be related to one of the colors that we saw previously on our electromagnetic spectrum. Okay, so here we see one of those equations we looked at before. Can we look at this equation and then figure out what has more energy, an electron in n equals 1 state or an n equals 5 state? Absolutely. So don't just take my word for it. You can use the whole ladder synopsis to help relate the concepts, but then if you wanted to actually calculate the math behind, oh, how much energy is in an n equals 5 versus an n equals 1, you could do that. And so what I want you to do is pause the video and calculate E for both an n equals 1 and an n equals 5. But hold on, so what is N and what is Z? So you know N is either 1 or it's 5, so calculate 2 E's. But then what about Z? Z is the number of protons. So if it's a hydrogen atom, you would look at the periodic table and remember that your atomic number is equal to the number of protons in an atom. And so if hydrogen is the first element, which it is, it has 1 proton. So Z is 1, N is 1, and then you would calculate your energy. Then you would do the same thing for an N equals 2. So you get for n equals 1, your energy is this value, and your n equals 5, it's this value. But these are negative, okay? And remember exponents. You may think, oh, well, man, that's 10 to the 20th. That's a big number. But no, it's not. To the negative 20 is a very, very small decimal. Remember, it's point and then a whole bunch of zeros, and then the 8th 7. How many zeros? 19. How many zeros in 10 to the negative 18? 17. And so it's actually a much smaller number for the n equals 5. So using this math, we get our n equals 1 is negative 2.178 times 10 to the negative 18, and our n equals 5 will get negative 8.712 times 10 to the negative 20. And so which one is closer to 0? Which one is bigger? We've got our n equals 5, whereas our n equals 1 is a lot more negative, and it's 10 to the negative 18 as opposed to the 10 to the negative 20 that we saw for our n of 5. All right, so how does this relate to the whole release of energy? Well, we have another equation here. So we have this one that we just looked at, and then we have another equation, and this is just for a hydrogen atom. This second equation is only for a hydrogen atom. That lets us relate as we fall from a energy level that's higher to an energy level that's lower. We can do this. So what if an electron falls from n equals 5 to n equals 1? How much energy is released then? Because I just told you you're falling from a bigger orbital to a smaller, therefore energy is going to be released. That release of energy is going to be in the form of light. All right, so we already know before from the previous slide these two values. We could do change in energy as E final minus E initial. Subtract your final, which is n equals 1, minus your initial, which was n equals 5, and you end up with negative 2.091 times 10 to the minus 18 joules. And remember, the negative refers to energy lost, so we've lost that amount of energy. We could do the same math using this equation on the right-hand side, where if my energy, my Z is 1, my N is 1, my N initial was 5, do all that math, put it into that one equation, and then we end up with that same value, negative 2.091 times 10 to the minus 18. Okay, so that negative simply is referring to energy that is lost. All right, so how does this relate to color? Well, remember, your wavelength is equal to hc over change in energy. And so we could have used either of these two equations here, and in doing that, we would calculate how much energy is released when you fall from a 5 to a 1 or a 5 to 2. And then we can relate that change in energy using Planck's constant and the speed of light to figure out what wavelength. And because of that wavelength, then we can figure out, is it blue, is it red, is it ultraviolet, is it infrared, just using the information that is contained within our periodic table and the equation that we did a second ago. Okay, so either you can calculate delta E from that equation, predict the wavelength, or you can say, oh, I saw blue light, how much energy is associated with it? And that's where we get the idea that red is less energy, violet is more energy. All right, so then back to those line spectrum we looked at before. This was the hydrogen line spectrum, and then our textbook has this picture here, which is a little bit misleading because if you actually calculate the transitions and relate them to color and energy, in this figure it looks like it's going, oh, from 2 to 1, from 3 to 1, and 4 to 1, but in actuality, those transitions are all super energetic and therefore in the ultraviolet region, and so we don't see them. So if you were to shine hydrogen light at a prism, these three colors that you see, they are not the 5 to 1, 4 to 1, 3 to 1 transition, because all of those transitions are super energetic and they're ultraviolet and our eye can't see them. Instead, it's falling from a 5 energy level to a 2, from a 4 to 2, and 3 to 2. Those are the ones that we see. Whereas falling from 5 to 3, 4 to 3, those have very small transitions, and so those are lower energy transitions, and what do you know, those are infrared. But how does all this help? Well, if you ever wanted to create a really beautiful fireworks display, for instance, you would be able to calculate what color do I want, turn that into energy, and then you could predict which elements, sodium, lithium, potassium, etc., would generate those line spectrums. Or you could just blow them up, see what colors you get. But this is the theory behind all of these things, and they will help us understand why elements eventually react, which is where we're leading up to in future chapters.